My name is Yurii, and I represent a group that builds an automated export system for pulsar data streams. And I realize that I'm unlucky to have the last talk of the day, so I'll try to not to bore you with a lot of technical details. So in fact, the main purpose of this talk is to advertise our work and to opening up a dialogue with other groups that study pulsars in hope to exchange ideas. So just, if you're interested in this, just talk to me later. Okay, so we call our project MLPPA. It's not much of a name, but it's short, and well, if you remember it, then you can access our work. So this is identified, basically. It stands for Machine Learning-Based Pipeline for Pulsar Analysis. You already know another member of our team, Andrei here, who is actually one of the main driving forces behind this whole thing. So this is a multi-institution project, and in addition to this institute and Bonn Uni, we also have members from AHTW Berlin and from Frankfurt Institute of Advanced Studies. And it's covered by two funding projects, Punch for an FDI and InterTwin. So Punch for an FDI we probably know about. It's a German project uniting many astronomers and particle scientists to apply various advanced computational methods. And InterTwin is actually a smaller European project that unites several groups doing work in physical sciences and environmental sciences, especially those that use digital twins, and in hopes that we can build some sort of unified framework that could be then be available to everybody and be applied in every field. So the motivation. We sort of walked into this one. I mean, we wanted bigger, better radio telescopes with more beams, with more everything, sensitivity, resolution. And so now they produce so much data that we can no longer apply our usual strategies of dealing with it. So, I mean, usually we used to keep the data indefinitely and then wait for PIs to decide if it can be deleted. Right now, not only we can afford, like with Meerkat, when it arrives now it can produce petabytes of data per week. So it cannot be kept indefinitely. It cannot be even kept for a team of quality assessment experts to work with it and analyze it. So the only answer to this is some sort of automated solution, computer pre-sorting that can throw away all the bad data and leave only what's interesting. So in addition to this, of course, because it's a big data problem, so not only this system should be automated, it also should be HPC capable, so high performance computing running on modern supercomputers and superclusters. And that's also a problem because modern radio astronomical software like CASA, for example, just doesn't run well on supercomputers. It's suited for like PC. So we need to build it from scratch. But there are good news too, because once we build such a system, we can apply it like during service, for example. So we scan the sky and we can teach our system to recognize a transient. So, and it just, when it detects a transient, it alerts team scientist, it triggers target of opportunity mode, and you can point other telescopes at it. So it's a good thing, so it's not all bad. In that case, this is just a simple system, so I'm just not going to go into all the technical details. We have the data stream. Oh, sorry. So we have, we don't have a pointer or something. So we have a data stream coming. So, of course, we first need to apply it for training of the system. Then, when the system is trained, we have a expert system that just sorts through it and assigns labels to this. And I will explain later why. Actually, we also need a digital twin So a special module that produces synthetic data. And as in our team, we basically split work into 3 parts. So one is empirical block. It's when we study actual data from the telescopes and build all kinds of tools to work with them. Then there is a theoretical block exactly for building the digital twin of the telescope system that observes a pulsar. And then there is a C++ development block because everything here is built in Python, but once we have good algorithms, we should implement them efficiently in C++. So when of course, an original shape, the data stream is just time series. But analyzing time series is difficult, so it's actually pre-processed, the Fourier transformed and transformed basically into a sequence of what we call time frames, small images which have time on one axis and frequency on the other axis, which allow to recognize easily various things like no signal, pulse, like pulse in this case, it's a characteristic dispersion shape that you all know very well, or various kinds of NFI. So these are the 4 basic types of time frames. So this is obviously a pulse. This is a broadband RFI over all frequencies but short in time. This is narrowband RFI over only some frequencies but covering a long distance in time, and then there is just not noise. Well, there is a problem. In real data, these things represented very unequally. So most of the data, you have nothing, then you have some small percentage of various types of RFI, and only like in typical data set that you have only 0.2, thank you, % of actual pulses. So that's why we need digital twins. Because to train the model, we need equal types of every representation of data, equal number of every type of data. And so we're doing this with the building a sophisticated model starting from the actual model of a pulsar, then propagating the signal through the ISM, applying various sorts of interference, going through the telescope electronics, and finally getting a frequency time graph. So you might ask, why can't we just look at this shape, the original shape, and just mimic it? I mean, it's just a simple curve. You can apply noise, you can model this curve. So yeah, of course we did this too. So we have another tool that does exactly that, the empirical tool. But as, I don't need to explain this because Lucy already explained this, that much more going on than just dispersion. So we hope later to be able to apply things like different beam shapes, different properties of ISM that would apply subtle changes in the final result that we will teach our system to detect, and then we will immediately get not only just, oh, it's a pulse, but something more about the properties. So, about the noise, obviously everything, we have a lot of noise, so we need to know what luckily, as you probably remember is your basic course of radio astronomy, the symbol radiometer model tells you that the noise is Gaussian, and it can be represented by a number of temperatures, of course, if everything works ideally. We did the statistical studies of our data, and so far, we are lucky it's exactly white noise, so we can happily apply the Gaussian model, but we'll be watching out for possible changes into like pink side. So now that we have digital twin, we can train the model on synthetic data, and this shows how it works. So it works fine when we have enough pixels in these 2D images. So you see like when 128 by 128, it's already pretty good. So this is our first release. As I said, if you remember, MLPPA, then you can go to GitLab and you can access all our software released now, and the 50-page paper that describes in detail everything. So it's designed, the C++ version is designed in a way that we have a Python Jupyter notebook as the input interface, and its all is within a singularity container, so at least theoretically, it should be easily deployed on any machine. Well, if it's not, tell us, please. If you try it and it doesn't work, we would be very interested to know. So, current activities and plans. So, well, we are using, at the moment, we are using some Ethelsberg data from different pulsars, including like crowd pulsar. In future, we plan to work a lot with Meerkat. Then we are now improving the physics-driven digital twin, like adding more complex beam shapes, improving ISM models, and so on. And with machine learning classifier, I already don't have time to explain, but we're improving low SNR performance, and we apply things like distributed training in Horovod, dispersion, transient peaks, and so on. So I'm skipping the details about how we fight the low signal-to-noise situation, and instead of conclusion, I mean, there are no conclusions. We are working on it, and we are hoping that we're going to improve our work. But I want to mention, this already has been mentioned today a few times, this recent discovery, but it makes our work, which is not just an exercise in computer science, but it actually can be applied to real jobs and looking for these quasi-periodic sub-pulse structure, because if you can just run it through the pulsar stream, we can detect all these subtle pulses in different ways. Thank you.
Thank you for finishing on time, Pranav.
Yeah.
Yeah, definitely in the future we are planning to apply polarization too. So, like, there are all ways and all directions that this model can be improved and made more complex.
Yeah, question?
Andrei, maybe you can answer this.
Yes, okay, but because there's a bit old results, we already have new results, but let me say it. So the accuracy is close to the 99%.
Great.
Yes.
That's really great.
Yes, but it's just for crop pulsar, I should say.
Okay.
When I add more pulses, we will see. Yeah.
Nice.
Yeah.
A question on that? Yeah.
So
So the digital twin is a classical model. So it just produces synthetic data. And the machine learning part is when you use this synthetic data to train the machine learning expert system, and then it just runs the neural network runs through the real data flow and labels it, tells you what it sees.
but at what
Pulse.
point of the analysis?
The idea is to create a system which has the minimal number of some processing with the data, work on the streaming, and has as many operations with the data as it possible. We try to apply train our model to work with the undispersed data, some pure data, to decrease the time processing. Because the idea is that we have a stream from the radio telescope, the insane rate, and we have no time to do the dispersion, another signal noise ratio. The pure idea have just baseband data, the buffer, And our model should find, here, there's a pulse. And we saved just this chunk with a pulse. The rest we will delete.
How much sensitivity do you use?
Well, the good question. I mean, you mean in sensitivity, what exactly?
Signal to noise.
Signal to noise, so our low limit right now is 7. We want to work above 7 signal noise ratio for the pulse, if it's possible.
All right. I think
You can just
thanks again for the talk.